Welcome to Ask and Learn.
We are given this reaction and we want to determine the partial pressure at equilibrium for carbon dioxide gas at 25 degrees Celsius. We can begin by writing out the expression for the equilibrium constant, Kp. We know that when we're writing out that expression, that solid species do not participate in that expression that we write out. If we have aqueous species, then we are looking for a value of Kc, since we have concentration values. But the only non-solid that we have in this equation is this carbon dioxide gas, and so we use Kp since gas concentrations are represented with partial pressure values. And so when we write out the Kp expression, we take the partial pressure of each gas on the product side of the reaction and we raise it to the power of its stoichiometric coefficient. And then we multiply that quantity by each gas in the products and then divide those same values for all the gases on the reactants. But since we just have one single gas on the product side, CO2, that means that the equilibrium expression, Kp, is just equal to the partial pressure of CO2, since it has a stoichiometric coefficient of 1. And so we know that there is an equation then to find the equilibrium constant using the change in Gibbs free energy of the reaction. So if we plug in values to solve for that value for the equilibrium constant, we know that that will also equal the partial pressure of CO2 at those conditions. So next we need to solve for the change in Gibbs free energy of the reaction. We use this equation on the bottom to help us do that. We first find the total change in Gibbs free energy of formation at standard conditions of the products and then subtract that same value for the reactants. We can break up the terms into the products and the reactants. And starting with the product side, we see that we have 1 mole of CaO and 1 mole of CO2. So 1 mole of CaO and 1 mole of CO2 are each multiplied by their values for delta G of formation at standard conditions, which we can look up in the appendix, so that units of moles cancel out to yield total units of energy for the change in Gibbs free energy of the products. And now for the reactants, we see that we have 1 mole of CaCO3. And when we multiply that with its delta G of formation at standard conditions value, we get the total Gibbs free energy change of the reactants. Then we take the total delta G of the products and subtract the total delta G of the reactants. When we do that, we get this final answer for delta G of reaction. And now we can plug that in for this variable in the equation that we are using to solve for the partial pressure of CO2. So Kp equals e to the power of negative delta G, which is what we just solved for, 130.9. And we need to convert this into joules so that we can eventually cancel out the units of the gas constant R. So we should multiply this by 1,000 to get it in joules per mole. Then we divide this by R, the constant 8.314 joules per mole times Kelvin. And then we multiply that by the temperature, which we are told is 298 Kelvin. And now we just plug that all in, and we know again from this relationship that equilibrium constant will be equal to the partial pressure of CO2, which is what we are ultimately trying to find. So we can say that the partial pressure of CO2 at equilibrium at 25 degrees Celsius for this system is equal to about 1.13 times 10 to the negative 23rd power in atmospheres for the partial pressure units.